We open now a new discussion on our sparse approximation problem and focus on the case where A is unitary. As you are about to see, this special case is very interesting and insightful. Since this part is a bit involved, we break it into two parts. We have defined P0 epsilon in this way, and we suggested the basis pursuit approximation of it, P1 epsilon. We also discussed their Lagrangian forms, Q0 and Q1 lambda. Our goal now is to learn how to solve these problems when A is square and unitary. That means that A has a set of orthonormal columns, and thus A transpose A is the identity matrix. Why are we dwelling on this question? Well, because for all these four forms, if A is indeed unitary, then the solution of these problems is an easy-to-obtain closed form. This is a source of inspiration, as it suggests that in this specific case, the P0 epsilon and Q0 lambda problems are not NP-hard anymore. Observe, by the way, that this discussion could not have taken place earlier when we presented P0, since P0 with a square matrix has no meaning. So let's start with Q0 lambda and develop a solution for it. We get now to the heart of the analysis, so please pay attention. This is the problem we start with, and you will all agree that it looks frightening. Exploiting the fact that A times A transpose is the identity, we can plug this expression in front of the vector B, and clearly we have changed nothing. We define A transpose B as the vector Z and replace it in the expression. Notice that Z can be computed a priori since A and B are given. Observe now that the multiplication by A in the L2 norm can be omitted since L2 is unitarily invariant. Thus, we get to this much simplified expression that says that we should search for the sparsest vector x such that it is not far from yet another vector, z. Why is this outcome so exciting? Well, because this problem is separable. It means that we can break it into a series of m separate problems, all sharing the same form, and each serving to get one entry from the unknown x. In general, solving one m-dimensional problem is much more complicated than solving m-separate 1D problems, and this is exactly what we got here. Let's zoom in on these 1D problems and see how we can suggest a solution for them. In fact, the solution of this problem is very easy to obtain. Notice that x, now being a scalar, could be either 0 or non-zero. If it is 0, then the value of the penalty is 1/2 times z squared. On the other hand, if x is non-zero, it might as well be equal to z, and then the penalty value is lambda. So obviously, we should choose 0 when its penalty is lower, leading to this outcome. The optimal value is 0 if z is small enough and z otherwise. So for the problem Q0 lambda, the solution is obtained by first computing z, being A transpose B, then applying the formula we have just derived for computing each entry in the unknown by thresholding. This is the curve that ties the values of z to their solution values. This curve is known as hard thresholding.